Okay, so the next type of induction problem is actually an inequation rather than an equation that we're going to prove. So 2 to the power of n will always be bigger than n squared, but you'll notice this time we're only going to prove it for n is greater than 4. Because if you think about it, when it's less than 4, it's not going to be true. Because 2 cubed is equal to 8, and 3 squared is 9. And don't know about you, but last time I checked, 8's not bigger than 9. So it's only going to work from once n is big enough, this will work. So the first case is n equals 5 for this one. Well, 2 to the power of 5 is 32. This is a left-hand side, right-hand side situation. 5 squared is 25, and yes indeed, 32 is bigger than 25. So yes, it works for the first case, n equals 5. So my assumption, and the other key part of this assumption, don't just say the result is true for n equals k where k is a positive integer. Make sure in your assumption you put in where k is a positive integer greater than 4, because that could come in handy, knowing that k is bigger than 4. So 2 to the power of k is greater than k squared where k is greater than 4. That's our assumption. We're going to prove 2 to the power of k plus 1 is bigger than k plus 1 squared. Now, there's different ways of doing inequalities. Some people like to move everything to the left-hand side and show it's always greater than 0. I'm going to do it this way. Let's have a look. 2 to the power of k plus 1. So I'm starting with 2 to the power of k plus 1. I want to show this is bigger than k plus 1 squared. Well, I know it's equal to 2 times 2 to the power of k. That'll allow me to get the assumption. And I assumed 2 to the power of k was greater than k squared. So I now know 2 to the power of k plus 1 is greater than 2k squared. Now I've got to keep an eye on what I'm trying to prove. I want to get k plus 1 squared. And if you think about k plus 1 squared, when you expand it out, you want k squared plus 2k plus 1. Well, I got k squared. So I'm going to split that up. I know I want the k squared. Now I'm going to play with the other k squared. K squared, of course, is k times k. And this is where I'm going to make use of the fact that k is greater than 4. Because k is greater than 4, I can say, well, k squared plus k times k is bigger than k squared plus 4k. Remember what I'm trying to get. K squared plus 2k plus 1. So I've got my 2k. I've got a bit extra, but I've got my 2k. Remember, k is greater than 4. Upside down triangle means because, for those that have forgotten. It's not used that often, so that's actually what that means. So, okay, I could rewrite that as k squared plus 2k plus 2k. Now let's play with the 2k. And again, I'm going to use the fact that k is greater than 4. So that would be greater than k squared plus 2k plus 8. Once again, because k is greater than 4. Remember, I want k squared plus 2k plus 1. And I guess this is the beauty of playing with an inequation rather than an equation. With an equation, what you do to one side, you must do to the other. You don't have to worry about that with an inequation, as long as the inequality sign is preserved. Because I can say, well, hang on a sec, I can take 7 away. Because if it's always bigger than this, if I take 7 away, it's still going to be bigger than what I got, because I'm taking something away. I don't have to do it to both sides. I can just take it away from the right-hand side. So I get k squared plus 2k plus 1. That's what I want. So I get k plus 1 all squared. And so there's my proof. If we read down, and notice how I don't put greater than on every line, because if you're reading this solution, you're saying this is equal to that, but that line is greater than the second line, but that line's equal to the third line, but that line's equal to the fourth line, but that line's greater than the fifth line. But as long as the inequality sign is preserved, so we never have a contradiction where one goes less than, one goes greater than, I can then look at that and say, well, hang on, therefore, 2 to the power of k plus 1 must be greater than the last line, k plus 1 squared. And hence it's true for k plus 1 if it's true for k, and now we can just induce. But remember, when you write it down, just don't blindly go, oh, since the result's true for n equals 1, because remember you didn't start with 1 on this one, you started with 5. And don't then blindly write, oh, then it's true for all positive integer values, because no, it was integer values of n is greater than 4.